Today we're going to be considering question 6 in section 1.2, which reads as follows. In an ordered ring R, the absolute value of x of an element x in R is defined by the absolute value of x is equal to x if x is greater than or equal to 0, and minus x if x is less than 0. Our goal is to show that the absolute value of x is greater than or equal to 0 for all x in R, and the absolute value of x is equal to 0 if and only if x equals 0. Then to show that the absolute value of xy is equal to the absolute value of x times the absolute value of y for any two elements x, y, and r. And finally to show that the triangle inequality holds in the sense that the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y for any x, y, and r. So take a couple seconds to try this out for yourself. Then we'll do some hints. Then we'll get in with the proof. Alrighty then, for some hints. I think the most important hint is to actually recall what the definition of ordered ring R is. Namely, that's a set where either an element is 0 within the set of positive elements of R, or within where the negative of an element is within this positive set of R. And that's a trichotomy in the sense that only one of them can be true. The next, we'll note that the positive elements are closed under addition and multiplication in the sense that for any two elements, A and B within P, A plus B is in P, and A times B is within P. And finally, we have that there's a linear order on the set in the sense that you can write A is less than or equal to P, A is less than or equal to B, which basically means for any two elements in the ring, either B minus A is equal to 0, B minus A is an element of P, or A minus B is an element of P, where P is the set of positive elements of R. I will note that these two options correspond to this one, but since we actually have trichotomy in this case, and you can read back to see where we show that, this means that this is the idea of equality, this is the idea of less than, and this is the idea of greater than, where these are A and B respectively. Finally, we'll note some important facts so that for any element, for any non-zero element, the square of that element is greater than 0. Note that 1 is greater than 0 in the ring, and then we'll note that for positive elements, scaling obeys the idea, let C be positive. We'll see that CA is less than or equal to CB for A less than or equal to B. And the converse, a similar identity is true, but if C is less than 0, you flip the inequality. Cool, with that, try to work on the proof for a couple seconds, and then we'll get into it. Alrighty then, for the first one, we're going to proceed by casework, namely that if we have a trichotomy, so this element x is either 0, positive, or negative. If x is 0, then you get the absolute value of x is equal to 0. If x is positive, then the absolute value of x is equal to x. And we see that x minus 0 is going to be equal x, which we said was positive, so this element of P. This implies that x is greater than 0. So we have, and then we note that x is the absolute value of x, so the absolute value of x is greater than 0. And finally, let's let minus x be an element of the positives. Then we see the absolute value of x is equal to minus x, which must be in the positives. And we check that minus x minus 0 is equal to minus x. And we said that since x was not in the positives and it was non-zero, then minus x is in the positives. So minus x is, minus x minus 0 is minus x, which is in the positives, which implies that minus x is greater than 0, which implies that the absolute value of x, which is minus x, is greater than 0. Next, let's do the second half, and we've already proved one direction, that if x equals 0, then the absolute value of x is equal to 0. Next, let's have the absolute value of x equal 0. Well, either x, by trichotomy, we either know x equals 0, is greater than 0, or is less than 0. And let's go through these cases. If x equals 0, then the absolute value of x is equal to 0, and 0 equals 0 is true. Next, let's let x be positive. We get the absolute value of x is equal to x. Let's let it be positive non-zero. Then the absolute value of x is equal to x, which if it were equal to 0, we'd have contradiction since we assumed it was non-zero. Therefore, x cannot be positive. And finally, let's let x be negative. If x is negative, then the absolute value of x is equal to minus x. And if this were equal 0, then we'd have a contradiction since we assumed that x was non-zero, so minus x is also non-zero. Therefore, we can exclude this case. There are a few other, perhaps better ways to prove this, but I think this is where we will proceed from now, by using these contradictions. For 2, we're also going to proceed by casework in the sense that if either are 0, x times y is going to be 0, and the absolute value of x, and without loss of generality, let x be the 0 one, then xy is 0, and the absolute value of x is 0, and 0 times any number, where y is going to end up being a positive number, is 0, so we get a true statement. So if 0 is true, then we have this equality. Next, let's try both are positive. Well, if both are positive, then xy is an element of the positives, so the absolute value of these two is xy, and then we'll note that it can be equal to xy, where this x is the absolute value of x, and this y is the absolute value of y. Next, let's have xy, x and y be an element of the negatives, or we say not positive except for 0. Then xy is going to be an element of the positives. Oops, x times y in this problem. Then we have x times y is positive. This implies that since xy is positive, then the absolute value of xy is just going to equal xy itself. Next, we have that if we consider the right-hand side, the absolute value of x is going to be minus x times minus y, and we've shown that within a ring these cancel in the sense that this is equal to xy, and we have xy equals xy, so we're done. Finally, if we have one of each, the most interesting case, we have xy, and let x be negative, I'm going to write that as negative x, is equal to the negative of xy. Perhaps that's a poor notation. Let's let x without loss of generality be negative. So if we let x be the negative of some number z, some positive number z, then xy is equal to negative zy, implying that the absolute value of xy is zy. And then we'll see that the absolute value of x is going to equal to z, and the absolute value of y is equal to y. So we get z times y is equal to zy, which is true. And we're done. Finally, let's proceed with the last statement, which is regarding a kind of version of the triangle inequality. For this, we're going to also proceed by even more casework. In this problem, let's let we're letting any x and y be in R. So if either x or y is R, or both, then we see this equality holds trivially because without loss of generality, let x be 0, then x plus y is just y, and that's equal to the absolute value of y, because that's the absolute value of y is always equal to the absolute value of y, because the absolute value of x is 0, and 0 plus the absolute value of y is the absolute value of y. So we're done. Alternatively, let's let x and y be non-zero. If they're both positive, then we have, if they're both positive elements, then we have x plus y, and then we take its absolute value of x plus y is just going to equal x plus y, and then we see this is equal to the absolute value of x plus the absolute value of y, because this is x plus y on the right hand side. Next, if they're both negative, we're going to have minus x, let's write it as minus x minus y for some elements z and w. This is going to equal the negative of minus x minus y, which is just going to equal x plus y by distribution. And then we see this is clearly equal to the absolute value of minus x plus the absolute value of minus y. Noting that in this problem we've replaced minus x and y with w and z in some sense. But we see this is equal to x plus y by itself, and we have equality. Finally, let's prove the most interesting case, which as a matter of fact we're going to have to prove by splitting into even more cases. Namely, let x and y be of opposite sign. This is the most interesting case. We've excluded all of the symmetric cases or all the zero cases, so we're left with this case. For this case, we have that x and y are of opposite signs, so let's let y equal to minus z for some z in the positives, and we're going to have x being positive. We split into the following cases. Either z is greater than x, or x is greater than or equal to z. If this is the case, and we'll note that z, you can also think about z, is equal to the absolute value of y. And then since x is positive, this is that the absolute value of x is greater than, this is the absolute value of x. So this would be the absolute value of y is greater than or equal to the absolute value of x. So let's consider that case first. For that case, we want to prove this equality, so let's consider a slightly different equality. Let's consider the absolute value of x plus the absolute value of y minus the absolute value of x plus y. This is going to give us, since this is just going to give us x plus z, and then let's look at this term, minus, and then x plus y. Well, we said that z is bigger than x. That means the magnitude of y is greater than the magnitude of x, or the absolute value. So that means x plus y, and y is negative in this particular case by supposition. Therefore, we have that x plus y is less than 0. That is, x plus y is less than 0. Therefore, the absolute value of some negative number is going to be negative if it's this. So we get this as minus, and we can call this x minus z. Given that, we can distribute through our minus signs, and we get this is equal to x plus z plus x minus z. And we see these z's will cancel out, and this is going to give us 2x. And we see 2x is greater than 0 since we supposed x was positive and non-zero. So we've shown that this relation is greater than 0, which implies that the absolute value of x plus the absolute value of y is greater than the absolute value of x plus y in this particular case. We'll note that we actually get the equality in the 0 or the symmetric cases. So that's why the full thing for any x and y includes the equality. But for now, we've actually shown that this is a strict inequality. Next, let's consider the complementary case. We're going to have them both be different signs, and we're letting, without loss of generality, letting y be negative. And in this case, instead of having z be greater than x, that is the absolute value of y, excuse me, is greater than the absolute value of y is greater than the absolute value of x. In this case, we're going to proceed with a slightly different assumption, namely the absolute value of x is greater than the absolute value of y. So I'm just going to flip these, this one and this one, which will then inform us when we're going to do the same trick as before. Let's consider the absolute value of x plus the absolute value of y minus the absolute value of x plus y. And we see that x is positive, so this can be x plus z minus the quantity of. And then here, since we have the magnitude of x is bigger than the magnitude of y, this is going to be x plus y. Because x plus y is positive, we're just going to leave it. And we note that y we can write as minus z. So we're going to write it like this. And once we do this, we see that this is going to be equal to x plus z minus x plus z. So it's going to be equal to 2z, which by supposition is greater than 0, since we assumed that z was positive, and we know that doubling a positive integer will give you another positive integer, and 0 is not positive. Therefore, we have that we have our inequality that this is greater than 0. So we've proven again the strict inequality that absolute value of x plus the absolute value of y is greater than the absolute value of x plus y. And with that, we're done. Thank you for watching and considering all this casework.